Okay.
Okay, perfect. Hello, everybody. My name is Mike Langton. I'm one of the senior applications engineers. I'm just going to do a very quick introduction and welcome everybody before I hand over to Jana for the main event. So welcome to this webinar, one of many that we've been producing recently. This one's based around geophysical investigations for geotechnical applications. Just before we get started, that you can communicate with us, should I say, at any point. And down that side of the screen, there is a chat box. So please feel free to ask any questions at any point. If there's any quick answers while the presentation is going on, I will do that. Any longer answers that might need a bit of a discussion, then we'll leave that towards the end when we will have a question and answer session. So, like I said, feel free just to ask any questions at any point. And you can also mark your questions as private if you don't want your name to be transmitted around the world, and we'll just highlight the question and answer that without mentioning your name. If for any reason the presentation freezes or Jana stops talking, and I always say this, and I say it for myself as well, we never stop talking. Please just at the top of the screen, there is a reconnect button. That is your best option just to restart the system rather than going out and coming back in again. It takes a little bit longer. So just hit that reconnect button a couple of times and just see if that fixes the issue with the connection. This session, like all the rest of our sessions, are being recorded. So if it does go drastically wrong with connections between us and you, then that will be made available a little later for you to watch that at your leisure. So, like I said, just say hello in the box, everybody. Let me know that people are out there. And with that in mind, I'm going to hand you over to the wonderful Jana. Jana has lots of experience in geotechnical applications, and I'm going to leave the full introduction to Jana. So over to you, Jana. I will disappear now towards the end, unless something goes wrong and I'll jump in. But otherwise, Jana, it's all yours.
Thank you, Mike. So today's webinar is Geophysical Investigations for Geotechnical Applications. And my name is Jana Gustafsson, and I have been working with the GPR and resistivity measurements for the last 20 years or so. Let's see. If I can find my presentation. I'm sorry for the delay. Can you see it?
Not yet.
Like that?
Perfect.
Perfect, then we start. So, the layout of today's webinar is about the history of geophysics in Sweden. I will give two examples on two larger infrastructure projects with geotechnical applications where geophysics have been used. And then we will have a quite extensive discussion on why we don't use geophysics and why we should use geophysics. And then finally, conclusions. Parts of this webinar was presented at the Near Surface Geophysics last autumn, and the work in this webinar was done during my years as a consultant at Turens AB. So let's start. We have a really long tradition of building and developing geophysical instruments in Sweden. For instance, ABM was founded already in 1923, and the ground of Malmö Geoscience was laid in 1936. but the use in practice have been really low in Sweden compared to many other countries in the world. And this depends to some extent on the first generation of users, especially for ground penetrating radar. In the 80s, when GPR was popular, the users claimed that they could find whatever the client was looking for. And this, of course, didn't work that well. We also have another explanation in form of geology. In Sweden, more or less 75% of the country is covered in till moraine. So this means really heterogeneous conditions. And of course, when we have these heterogeneous conditions of the geology, this is harder to explain with geophysical investigation techniques, but it should not be impossible. So fortunately, for the last 10 years, we have had an increase in the use of geophysical investigation methods as a complement to traditional geotechnical borings. And one of the main reasons for this is not the fact that geophysics have been more fancy or popular, but actually how the geotechnical engineers are working. They use more and more 3D models as a planning tool. And with this, there is an increased demand of more input data to create a good visualization of the subsurface. So with the 3D models, there's also an increase of more data coverage. And then, of course, geophysical investigation techniques can provide that data coverage. So my first example of a big infrastructure project in Sweden is called the Southwest Link. It's a high voltage cable in the ground. So it was 150 kilometers to be investigated with a really tight time frame. You can see the location of this high voltage cable in southern parts of Sweden. And for this project, we had a client with really large interest in geophysics. They have tried the technique before and actually liked the result. So over these 150 kilometers, 90 kilometers were investigated with ground penetrating radar. And ground penetrating radar was chosen as method because the investigation were quite shallow, down to say 5, 6, 7 meters. And due to the tight time frame and long stretches to be investigated, the GPR is the most efficient method to use. So the results from the ground penetrating radar measurements gave a really good input for the planning of optimal locations of the coming geotechnical investigations, and also, of course, provided with input both to bedrock and peat models. During the project, there was a discussion on how certain or uncertain is geophysical result compared to geotechnical result. For instance, the interpretation in form of accuracy of levels and what types of layers we actually see with geophysical methods. But also, how do we actually position our ground penetrating radar lines when our GPS system doesn't work? Concerning the level of accuracy, concerning the depth, it was not always in the same limits between what a geophysicist and a geotechnical engineering would like. They don't speak the same language because, and this should have been addressed prior to the project. A geotechnical engineer wants sometimes millimeter accuracy compared for a core for a bedrock level compared to what a geophysicist can provide. So there's a lack of understanding that a geotechnical drilling is precise in one point, while a ground penetrating radar actually measures in a volume and gives a mean value of the bedrock level in that volume. But for the result, the first one is the ground penetrating radar for the bedrock. And as you see, we have a green line for the interpreted bedrock level. So ground penetrating radar was done first of all and was used as a planning tool for the geotechnical drillings. So the drillings were placed in areas where the ground penetrating radar didn't provide any information, and of course also in areas where the uncertainty of the interpretation was lower. So instead of having these even traditional 200, 120 meters between your geotechnical borings, those are placed in a more optimized way when you can have some input from ground penetrating radar. And ground penetrating radar was also used for peat areas to look at the depth and the extent of the peat. And some of these peat areas were actually so wet, so huge machines couldn't go out on the peat without sinking. So the geotechnical investigations were to be done with handheld equipment, and sometimes, as you see, they didn't even reach the bottom. So ground penetrating radar was really effective in looking at the extent of the peat. So very important input from the geophysical investigations. Ground penetrating radar was also used to look at obstacles in areas where the high voltage cable were to be done by directional drilling. So for instance, this was a flat field, looked like quite clayey, and but the ground penetrating radar revealed that okay, below this flat green area, we actually have a peak of moraine coming up. So in this case, they could choose another way for the directional drilling. And if looking at a comparison between a normal geotechnical program for these 150 kilometers planned in a traditional way, we should have soil rock probings, maybe 800 points, stick sounding in peat, over 5,000, and also disturbed sampling in more than 500 locations. And in the project, the numbers that was actually performed were quite lower. And you can see, especially in the peat, there was a huge decrease in the number of stick soundings. And so ground penetrating radar done first actually saved approximately 2 million crowns back in the days when the investigations were made, just in field investigation money. So in this case, the use of geophysics also showed in real money. Then we have the other example. It's called the East Link, and it's a high-speed railroad between Stockholm and southern parts of Sweden. The first part, which is investigated now, is only 30 kilometers in quite close to Stockholm. But as this is in the planning stage, there were several different location possibilities from start. In parts, as many as 5 different corridors or lines for this high-speed railroad. And as you can see, several different geophysical investigation techniques were used in this project. And this was, of course, depending on different purposes of the investigations, but also on the very varying geological conditions along these 30 kilometers of high-speed railroad. And compared to the other project I talked about, in this project, the client's project group did not recommend geophysics at all. They were not that familiar with the technique. They hadn't used it at all. So instead, the head of technology at the consultant company was interested in geophysics and actually convinced the client to use the method. And this was due to the fact that the consultant wanted a non-destructive and fast way of investigating these several line options. As I said, in parts, 5 different corridors. So they needed a quick way of gaining data. And the area investigated is very topographical, with dense forest, and also with presence of nature preservative areas and archaeological sites. So to go out with the drilling equipment for these 5 different lines in this early planning stage would have been really expensive. And also in parts, the railroad is tunneled, so the depth to bedrock was essential already at an early stage. And then geophysics are fast and non-destructive way of gaining data. So the geophysical investigations gave answers to these critical questions of, for instance, rock coverage for the tunnels, and above all, contributed with dense data to a 3D bedrock model. Geophysics was made first of all in many parts, and without the knowledge from geotechnical investigation, the process to achieve reliable results was very iterative. So measurement, interpretation, and then reinterpretation in several rounds as geotechnical information continuously was gained. So this iterative process resulted in a complete picture as possible of the subsurface condition, but also led to discussion with both the planners at the consultant side and with the client on why results actually change. So again, a lack of misunderstanding between the geophysicists and the geotechnical engineers and the planners. What type of data do we actually gain, and how is the interpretation made? And during the projects, a lot of discussions were also held on the difference in, for instance, resolution and work pace for different type of geophysical investigations. Why do GPR resolve thin layers? Why doesn't it work in clay? How good is resistivity to use in thin layers? And so on and so on. So both sides learned a lot during the process of how we should actually speak between geophysicists and geotechnical engineers. So we understand that this method has these limitations and these benefits. In the project, as I said, the geology was very varying. We had plenty of high parts with some till and outcrops, and then we had the lowland areas in between with the clay layers, peat and till. So for the planning, to be efficient, we used ground penetrating radar in the parts with till and coarse grain material and the bedrock, and then resistivity in the parts with clay. So the correct geophysical method for the correct geology to gain a complete picture of the subsurface. This is just a short example of a resistivity profile, electrical resistivity tomography, measured with 5-meter electrode spacing. And as you can see, the low resistivity areas in blue indicating clay, and then we have a part completely red indicating a upcoming bedrock. So resistivity was perfect for the deep investigation where we had the clay on top. And it was used to resolve both the amount of clay and then the underlying moraines, and finally the bedrock level. And as a bonus in this project, resistivity proved to be able to, in a very nice way, map also fracture zones, which of course was very important in the areas where tunneling of the railroad was planned. This is an example of ground penetrating radar data. You have the bedrock interpretation in red, and then a peat area in green. So first interpretation, and then planning of geotechnical borings. And when the borings was ready, again, a new interpretation round for the ground penetrating radar, as well as for the resistivity results. So you can actually see that the red line it's of course changing when we gain more information on these important point-wise geotechnical investigations. So both these huge infrastructure projects led to a process that I think is quite good to have when you use geophysical investigation techniques for geotechnical applications. Start with geophysics, more or less always, I should say, because you have a fast method of gaining good information of the subsurface. If you don't know anything of the area, always start with some type of geophysical investigation technique. Do a interpretation of the data gained, sometimes with most often without any other information, but just look at the geophysical data and create a subsurface model of the geological conditions. And use this information as a planning tool for the geotechnical investigations. Most often geotechnical investigations like boring are quite expensive. So the points need to be placed in a good way where they actually give the most data amount possible. For instance, if you do ground penetrating radar investigation in a moraine area and you know that, for certain that, okay, this is an outcrop and I can follow this bedrock surface, there's no need to do drilling in that area. Then it's better to place the drillings in areas where you have more complicated geological conditions, as clayey moraine or very several layers of different types of soils. And when you're ready with the planning of the geotechnical investigations, you carry out these as field measurements, drilling, core sampling, digging, whatever. And this information goes back to the interpretation of the geophysical data. And this can go round and round for several times, because sometimes you understand that, okay, with this input, we actually also need more input in this area. So this is the iterative process to make as good as possible interpretation of the geophysical data. And both the interpretation of the geophysical data and the interpretation of the geotechnical data gives data to both 2D and 3D models. And most often when you build, for instance, a bedrock model, the geotechnical data is the most certain and should also be treated as the most certain data input. And then geophysical data is the second, and that's your building stone for instance, a bedrock model. And those can look differently depending on if it's in 2D or 3D. But to create the right-hand side picture in 3 dimensions, you need plenty of point-wise data, or you need point-wise data combined with geophysical data, which gives much better coverage. So you need both. You need both the points, and you need the coverage you gain from geophysical investigations. But why do we not use geophysical investigations for geotechnical applications in all our geotechnical projects? In Sweden, since the start, we have had a large number of bad examples. Geophysicists have tended to promise 100% of data, but of course they fail to deliver, and this leads to mistrust and disbelief in the methodology. And there's also the fact of uncertainty. The results from geophysical investigations are dependent on several different factors. The field conditions, the experience of the interpretation, the physical contrast, disturbances in the surroundings. We do measurements in volumes of soil, and these uncertainties needs to be clarified prior start to get an understanding for both geophysicists and the geotechnical engineers. So I think that most often the coverage of reliable data is not 100%, but maybe 40 to 50%. But still, and that's also needs to be addressed, that we get more information, but we will never have 100% unless we actually dig the whole complete area. And finally, we have the problem of data format. How are the results from geophysical investigations fitted to geotechnical information and planning softwares as CAD? Today, I think that there's often a lack in this chain where we actually give geotechnical engineers data that they don't know how to further process. And this is the more positive side, why do we actually use geophysical investigations in geotechnical projects? Because we need to do it, and we need to do it even more. The first one, efficiency, both in time and economically. For instance, when we have several choices of lines in a planning stage, we need quick information without extensive preparation, as for instance, clearing for a drilling machine. Then geophysical investigations are outstanding. We also get extensive data coverage compared to traditional point-by-point investigation. And this is today a requirement when we are working with the 3D models of, for instance, the bedrock. We get an overview, as one of my former geotechnical engineering colleagues said, that geophysical investigation is my extra pair of eyes. I think that's quite nice. And of course, geophysical investigations are more available because they are non-destructive and can be used in almost any terrain, even in dense forest, in large topographical variations, where drilling equipment has hard to move around. And we can also use geophysical investigation techniques in nature preservative areas or on archaeological sites where you actually can't destroy the ground. So efficient, good data coverage, we get an overview, and the methods are available. But to even more promote the use of geophysical investigation techniques, I think that we need to address these points. We need to specify the purpose of and the expectations of the geophysical investigation at an early stage, so that both the geophysicists and the geotechnical engineers understand what we are doing and how we are doing it. So an awareness of the method itself is also needed in terms of how it works, how do you do it, and this to gain an understanding of which factors may impact the results we actually gained. We need to be more open in the discussion of uncertainty. It needs to be open and clear. And this can, for instance, be made by showing a span instead of a single line for bedrock interpretation, or give different weights on classes for the interpretation made. Maybe really certain, not that certain, not at certain at all. So we actually address that this is an interpretation with the different certainties. We also have the discussion on standards. Today, geotechnical methods and results from geotechnical methods are completely standardized, but geophysical data is not. So that's also a question of what type of data do we gain, what do we do with it, how can that be fitted into something else. And finally, the tools. Tools for interpretation and visualization of both geophysical or geotechnical data are found in, I don't know in how many numbers, and these are seldom compatible. So we should use the same tools for both geophysical and geotechnical data, or any data from the ground. So we get a complete visualization and can make the correct assumptions of the ground conditions. These 5 points, I think it's quite important to address. when we want to promote the use of geophysical investigations for geotechnical purposes. And conclusions, hopefully there is a bright future. Maybe I should change that to say that there is a bright future for geophysical investigation techniques. And I actually hope and think that geophysics should be a natural part of the toolbox when we are investigating the subsurface conditions, and especially as a really efficient starting method, the extra pair of eyes. Thank you.
I think that highlights quite a few important things there, Jana, that it's not just about having an instrument and a person to give the answer, but we also need additional information like the field measurements, core samples, etc., to feed back in to help with interpretation.
Yeah.
And this is one of the key things. And also the education towards the very end client who's requesting this information. And to limit their expectations, to manage their expectations in what they're going to get, and to what confidence level that we're able to provide. I think that highlights quite a few points there to think about. We had one question from Francisco, who asks, what frequency did you use in the southwest example? I think it was one of the first examples.
Okay, in that project we used a ProX system with 250 megahertz antennas for the parts in till and sand, and then for the peat areas we used an RTA 100 megahertz antenna.
Perfect, excellent. I think, Joseph, if you can just type your question into the text box, if you can. And then we had another question from Andreas, who's asking for an e-certificate. And I think that's something that we haven't provided before in the past, but that's something we maybe need to think about, particularly for continual professional development. So we'll have a look into that at some point. And also, Andreas asked if you can get the paper or literature from the event. I think we'll discuss that afterwards, and see what we can provide there. So Joseph asks, can the interpreter of the GPR data also interpret the resistivity data as well?
Yes, it's the same iterative process for resistivity data that it's for ground penetrating radar data. We do the resistivity measurements and do an approximate interpretation of, for instance, the bedrock level. But as fast as we gain information back from the field, the point-wise drillings, we do a reinterpretation of also the resistivity.
I think it's also down to the experience and the training of the person as well, obviously, to whether they can interpret resistivity and GPR. I think that's a critical factor. Okay, I guess we'll just wait a few more seconds or so just to see if there's any more questions coming in.
Yes.
Hariri asks, geophysical results at tropical countries, maybe not easy like Malaysia. It really depends on the water content, moisture content in the ground.
Yeah.
This is one of the critical factors on which technique that we're going to use. Some techniques allow us to use in moisture-laden soil, and others maybe not as much so. So it's not just about, I would say, just that one instrumentation. Sometimes a different instrumentation may be needed in different areas.
Yeah, and I said that geophysics is one tool. So actually, geophysics is several tools depending on the soil conditions. And we also need to understand that sometimes a combination is the best. As in the case of the East Link, that use resistivity where you have clay and use ground penetrating radar in coarse-grained material, because of course ground penetrating radar is much faster than the resistivity, but it doesn't work in clay. So we have to use both.
Absolutely, it's like going to do some job around your house. You may not just take one tool to do that job. You may need multiple tools to complete that task, and
Precisely.
very much so with geophysics, and to compare the different results to get the answer.
Yeah.
We have a question about GPR horizontal resolution. That is dictated by the frequency, is the horizontal resolution. So it really depends on the frequency of the antenna. Higher frequency will give you better resolution, but that often leads to less penetration. So there are tabulated values and also calculations for the horizontal resolution. That's something calculation-wise we can provide that equation if you require that. I think we've answered one of those questions.
Can we use ground penetrating radar for profiling some surface soil layering under concrete foundations? I have done it, but that's a question of how the foundation looks like, how thick it is, and how much rebars you have in the concrete. Too much rebars and too thick concrete will decrease the possibilities to look at the subsurface layering. And most often also when working inside of buildings, you actually can't gain that long profiles. And to do a good interpretation of ground penetrating radar data, the profiles can't be like 1 meter long. Then you can't actually see any structures.
Tobias asks the question, is it an option to combine GPR and resistivity, not necessarily joined inversions?
Is there an option? No, because we
can combine the interpretation.
Yeah, you can combine the interpretation if you you work in some type of 3D model world, but otherwise the inversion is completely different from ground penetrating radar or resistivity. So we can't put the results and do the processing interpretation in one software. We need two, but then we can. But in 3D models, we actually could take in ground penetrating radar data and resistivity data and do the interpretation in some sort of 3D CAD, for instance.
Eunice, these questions probably sidetracking slightly, but still important and one that we can answer. And what's the difference between the ProX system sampling and the GX HDR system? How much difference in the RD3 and RD7 data?
Maybe we could take these by email instead.
I think that would be a good answer to that one. Yeah, I think, Eunice, if you can email myself or Jana, I'll just put my email address in the box. Drop us a line and we will answer that one separate from this. Yeah. It's a long explanation, is that one?
I can type in my...
Is it possible to change the time window in the GX? Yes, you can. That's in the settings. Again, we'll answer that outside of this.
And there was a comment on clay. Yes, clay is difficult and it differs. So you never know if you can use ground penetrating radar for clay or not, but most often not. Sometimes in Sweden you can penetrate like half a meter of clay, but sometimes 2 centimeters of clay is far too much.
I think the moisture content there is obviously a very critical factor on
and
that.
And also the minerals within the clay.
Okay, Francisco, we'll discuss that question of the slides of the presentation, and we'll email you that afterwards. Hariri, weakness of GPR is water. That is one of the critical factors, though we can use GPR over freshwater lakes. So it's a combination of the water and the soil itself that's the issue on that one.
Yeah. If you have fresh water, groundwater in a nice sandy environment, it doesn't affect the ground penetrating radar at all. But if you have the same water with this minor amount of salts, you don't see anything. So it's always the combination of the water and the content in the water in form of dissolved ions.
Andreas asks why electromagnetic or GPR wave transmits like an acoustic wave. Electromagnetism and acoustic waves are forms of energy and transmit in a similar fashion. That's another long explanation, I think, that could be taken. We have that in our theory booklets, so that's something that we can send over to you as well afterwards. I think that's a longer explanation that's needed on that one.
Yeah.
We're here to help. We are a part of our job is to assist and answer questions like this, and we're quite open and quite happy to receive questions. So anything technical, like some of these questions, please feel free to drop us an email. Sometimes we have some good documentation explaining the principles and theory of GPR and the other geophysical techniques. So please drop us a line and we'll send that information out or answer you personally on those questions. Can you see that last question there from Joseph?
Maybe I changed my mind of what I was going to talk about after I made the name of the webinar. I'm sorry. And both of the examples are actually geotechnical investigations in the first place for building both high voltage cable and high speed railroad.
Okay, we've got a private question there. I think we'll answer that one again afterwards.
Yeah. And I hope you can see my screen because I just want to say that you can also join us at GSA 2020 for 2 short courses, one on resistivity surveying and one on geophysics for geotechnical site investigations.
Perfect. We also have some additional webinars coming up. I think the next one's on the 24th of September, and that will be a discussion of arrays, and in particular the MIRA multi-channel array systems for large collection of data over dense data collection over large areas. So that's one to watch out for as well in a couple of weeks' time. That's coming up soon, so just keep an eye out on the posts, etc. for that. Okay, so I think we'll wrap it up for now. Thank you very much for everyone for attending. We had some really good questions there, and I think Jana raised quite a few interesting points throughout that session, particularly think about from the end user's point of view and the education that's needed from that as well. So thank you very much for attending once again. You know where we are if you've got any questions or any additional comments. So for now, thank you very much. Stay safe, everyone, and we'll hope to see you soon.
Thank you.